everyone. I'll stand a bit closer. I'm Sabrina Berger. I'm a PhD student at the University of Melbourne, where I work with Stuart Wythe and Madeline Marshall on a project looking at how we can train the properties of high redshift quasar hosts with the James Webb Space Telescope, or JWST. So this is an artist depiction of a quasar. Really beautiful artist depiction, of course, and it has a nice jet coming through it. So quasars are a subset of active galactic nuclei that are ultraluminous and ultramassive and highly accreting. So we're mostly interested in high redshift quasars. So these are quasars with redshifts greater than about 6. And again, those are ultraluminous and highly accreting supermassive black holes. And because they're so massive, they have really mysterious formation histories. How did something so massive form so early on in our universe? And to be able to answer questions and explain how that happened, we need to be able to better constrain the stellar mass to black hole mass ratio. And we can kind of do that in the sub-millimeter. We can trace the cold dust of high redshift quasar hosts, but that just gives us a dynamical mass that isn't very accurate. So to be able to do that accurately enough to constrain our models, we need to observe these quasars in the near infrared, or the rest frame optical UV, so that we can actually disentangle the stellar and quasar light for more accurate measurements of stellar mass, radius, and other properties. So this is a luminosity function, actually it was published just a couple weeks ago, showing just how rare these high redshift quasars are. So as you go down from Z equals 4, you can see they become more and more infrequent. And of course, when things are rare, that makes them much harder to study. So why JWST? So it was launched in 2021, and it has already had immense impact on high Z science, as we've heard previously, and we'll continue to hear about in the rest of this session. And it has a much higher resolution than Hubble. And this reminded me when I was at Rottnest Island a couple days ago with Aman and Matt, who are seated over there. Just when I was looking at their images, comparing the iPhone camera to Aman's huge lens, just the kind of difference in resolution that we can get even from wildlife images. So I thought that was kind of analogous to the difference in JWST and Hubble images. So you can see that galaxies that looked just kind of like blobs now have these resolved spiral arms and spiral bars, which is really exciting. And it's allowing us to peer deeper and deeper into the high redshift universe and understand more about how these galaxies formed. And also causing a lot of contentious arguments about who's found the highest redshift galaxy. So NIRCam is currently the best instrument to image these high redshift quasars, and it observes between 0.5 to 5 micrometers. So this 150W filter is just one example. It has 29 filters, but I'll just be talking about 2 today. So despite having a higher resolution with JWST, it's still not that easy. We still need to be able to carefully model off the quasar's light and subtract it off from its underlying host galaxy. And I'll talk about that model a bit more detail in a couple slides. But you can see at Z equals 2, this is the quasar image that we detect and do some fancy modeling. And then when we subtract the point source or the quasar, we're left with this nice underlying host galaxy. This is the smooth version. But at Z equals 6, so this is for quasars that we tried to detect their host with Hubble. You can see when we do that same process, we're left with just a blob. We're over subtracting basically, and we don't have the resolution high enough to actually detect the underlying host galaxy. So we could only set upper limits on the infrared emission with high Z quasars that we observed with Hubble. And luckily, we have JWST to hopefully get the resolution that we need. So they kind of beat us to the chase, or my co-supervisor to the chase, and detected 2 high redshift quasars last year with JWST. So this was J2255, which was detected just in the F356W filter, and then J2236 was detected in both filters. And both these quasars are about redshift 6.5. So you can see these images. This is a larger view of around the galaxy and the very important PSF star that will be important when we talk about imaging these quasars and actually subtracting the point source. So with any good observation, we always need to have simulations to go along with them. So the blue tide simulation provides us with an excellent model for high Z quasars that we can then compare back to our observations. So blue tides is a full hydrodynamic simulation that was run between Z equals 7 and Z equals 99. It has huge amount of particles, so 7,040 cubed, and it's about 400 megaparsecs on each side. It has 200 million star-forming galaxies. So you might begin to think, okay, all these galaxies, there's got to be some of those that have quasars that we can compare our observations to. And we take 108,000 of the most massive of those black holes to actually plot out the distribution and compare them to our observations. And blue tides include some really accurate physics, which includes star formation, feedback processes, and black hole accretion. So that's really good. We're making sure that we're getting the most accurate simulations of our early universe that we can get, at least currently. So these are some of our initial results. Basically, what I've done here is just overplotted the observed quasar host properties with the blue tides distribution properties. And you can see that these high Z quasars that were observed with JWST sit sort of near the higher luminosity edge of the blue tide distribution. But still, these quasars actually sit pretty in line with the blue tide simulation's properties and have values consistent with them. I'm only showing here the black hole to stellar mass ratio, but we've also done this with black hole accretion rate and other properties. And then we can also, which is really exciting, start to make predictions for other properties of these quasars. For example, the star formation rate. We need follow-up spectroscopic measurements to actually do that properly. We can kind of make a prediction that the star formation rate will probably be about 10 to the 2 or 3 solar masses per year, and use that in our future work before we get observations. So the next thing I did was, I guess, a bit more of a qualitative approach, which then leads to some quantitative measurements. But we needed mock imaging to be able to compare our blue tide simulation quasars to the actual quasars that were observed. So we observed something like this, and then we use MCMC, or your favorite sampling method. Ours is just MCMC. And we sample from this joint probability likelihood. So for basically the summation of the image values at a particular pixel, what's the parameters that describe the host galaxy and the point source well? And then we fit this convolved model, which is this nice looking kind of noiseless image because it's perfect at this point, which has the underlying host, the quasar, and the PSF convolved on top of it. And then with that in hand, we know what the point source is supposed to look like, the image point source, so we can subtract off the point source from the data to get our final result, which should just be the underlying host galaxy. So we've done this with a bunch of quasars that have similar bolometric luminosities to the JWST quasars that were observed. And so we're in a really nice place because we can actually image the galaxies in blue tides without the point source and compare them. So we have an idealized version of what the point source subtraction should produce. So these two images, to me, look pretty similar. So we're doing a pretty good job. We can also then measure the effective or dust attenuated radii and compare that for the data minus quasar and the galaxy only image, and kind of compare those to see what adding the point source and what our point source subtraction algorithm actually, how it affects our measured effective radii. So to summarize, we have some newly observed quasar hosts that are in line with our blue tide simulations, which, as you might have seen, was from 2015. So despite being 8 years old, this simulation is still doing really well and predicting accurate properties. And our mock imaging pipeline recovers accurate galactic radii post point source removal, which is important for our next 2 steps because we're getting the JWST observing window for my co-advisor is currently open right now. So we'll get new NIRCam images of higher luminosity quasars in the next few weeks, and hopefully we'll be able to detect the quasar host with those new quasars, and then continue to answer questions like, how does the observational bias affect our radius measurement, which again, we're well equipped to do with the blue tide simulation and our mock imaging pipeline, and then of course, how accurately we can constrain the black hole to stellar mass ratio, and continue to try and understand how these early universe black holes evolved to become so massive so quickly. So that's it. I'll take any questions. you.